begin and where does it end? Could the very existence of life, stars, and galaxies hinge on a delicate cosmic imbalance? To understand why the universe as we know it exists, we must first unravel the principles of balance, principles that govern not just our world but the entire cosmos. The foundation of reality, as we understand it, relies on a principle as ancient as time itself: balance. Energy can neither be created nor destroyed, it simply changes form. For every action, there is a reaction. What goes in must come out. This principle, rooted in the conservation laws of physics, dictates the behavior of everything from atoms to galaxies. In the 17th century, Italian physician Santorio sought to explore balance within the human body. Driven by curiosity, he embarked on a decades-long experiment. For 30 years, he meticulously weighed every liquid and solid he consumed and every excretion he produced. He weighed himself before and after physical exertion, keeping a daily record of matter in, matter out. Yet, Santorio encountered a puzzling mystery: the mass of his excretions never matched the mass of his food and drink. It was as though the human body, like a campfire, consumed matter and left behind something far less substantial than what it had started with. Santorio's instincts were correct. Matter does not simply vanish. By the 18th century, natural philosophers proved that the total mass before and after a chemical reaction is conserved. This revelation illuminated the workings of metabolism and combustion. Whether breaking down food into fats, proteins, and sugars or burning wood into ash, carbon dioxide, and water, every chemical equation balanced out. Atoms merely rearranged themselves, ensuring that the total count remained constant. Yet, even as this principle held true for most reactions, the universe itself began to challenge its own rules. The sun, the very source of daylight, provided a paradoxical clue that balance might be more complex than it first appeared. In the 20th century, humanity unlocked the nuclear secrets of the atom. Deep within the sun's core, hydrogen nuclei fused to form helium, releasing immense energy in the process. However, the mass of the resulting helium is less than the combined mass of the original hydrogen. The reaction seemed unbalanced. Where had the missing mass gone? A young Swiss patent clerk, Albert Einstein, provided the answer with his revolutionary equation. Mass, Einstein revealed, is not an isolated property but a form of energy. The missing mass from the sun's reactions is converted into photons, the sunlight that illuminates our days. Balance, though subtle and transformed, is ultimately restored. If the universe tends toward balance, then why does it seem so profoundly unbalanced? Nearly everything we see, touch, and experience is made of matter. From the atoms in our bodies to the stars in distant galaxies, the universe is overwhelmingly composed of matter. Yet, for every particle of matter, there exists an almost identical counterpart, antimatter. Antimatter particles mirror their matter twins in mass but carry opposite charges. According to the laws of physics, the Big Bang should have produced equal amounts of matter and antimatter. When matter meets antimatter, the two annihilate each other, releasing pure energy. If the early universe began in perfect balance, with equal parts matter and antimatter, then why is there such an overwhelming abundance of matter today? Where has all the antimatter gone? The imbalance between matter and antimatter is one of the most profound mysteries of modern physics. Without this asymmetry, the universe would be a vastly different place. No stars would shine. No planets would form. No life would exist. The cosmos would be a void of light and structure, filled only with radiation from matter-antimatter annihilations. Yet, the observable universe defies this fate. Somehow, in the earliest moments after the Big Bang, a subtle asymmetry emerged. For every billion particles of antimatter, there was 1,000,000,001 particles of matter. The excess matter survived annihilation, seeding the formation of galaxies, stars, and planets. This imbalance, infinitesimally small yet cosmically significant, is the reason we are here. How did this imbalance arise? Scientists have proposed various mechanisms, including processes known as baryogenesis. These theories suggest that tiny differences in the behavior of matter and antimatter, governed by the weak nuclear force, could have tipped the scales. Experiments, such as those conducted at particle accelerators like CERN, continue to probe the fundamental properties of matter and antimatter, searching for clues to this cosmic puzzle. As we gaze into the night sky, the vastness of the universe confronts us with its apparent contradictions. A cosmos that began in perfect symmetry now teems with imbalance, its laws both balanced and unbalanced in ways that sustain complexity and life. This paradox lies at the heart of existence. Why does the universe appear so perfectly balanced at its inception, only to evolve into a realm where imbalance gives rise to structure, light, and life itself? The journey of antimatter, from theory to discovery. The story of antimatter is one of the most fascinating and fundamental chapters in the history of physics, intertwining theoretical breakthroughs with experimental triumphs. The most famous equation in physics encapsulates the relationship between mass and energy. In this equation, represents the ultimate speed limit of the universe, the speed of light traveling unimpeded through the vacuum of space. Simple in appearance, this equation underpins Einstein's theory of relativity, which reshaped humanity's understanding of space, time, and energy in the early 20th century. This era marked a revolution in physics, where concepts once unimaginable began to reveal the universe's secrets. Among the brilliant minds of this transformative period was Paul Dirac, a theoretical physicist from Bristol. Dirac's contributions would not only extend Einstein's insights but also uncover an entirely new realm of existence. Born in 1902, Paul Dirac's journey began with engineering studies before transitioning to mathematics, earning his PhD from Cambridge in 1926. Known for his precision in thought and speech, Dirac's retorts during lectures were as incisive as his scientific insights. To fellow physicist Niels Bohr, he once advised, "Never start a sentence without knowing the end of it." By the mid-1920s, quantum mechanics was revolutionizing our understanding of the subatomic world. Electrons and protons, the only known particles at the time, could be described both as particles and waves. In 1926, Erwin Schrödinger published his foundational equation describing quantum systems. Yet, as Dirac examined this new framework, he realized it was incomplete. Schrödinger's equation did not account for the effects of Einstein's relativity. Dirac set out to unify quantum mechanics and relativity. His work culminated in the Dirac equation, a more comprehensive mathematical description of particle behavior. Years later, when asked about his groundbreaking discovery, Dirac's response was characteristically succinct: "I found it beautiful." Dirac's equation revealed a startling implication. While electrons had been understood to exist only with positive energy, the mathematics suggested they could also possess negative energy. This posed a problem. If negative energy states existed, electrons should continuously spiral into them, emitting infinite amounts of light in the process. Clearly, this was not the case in the observable universe. To resolve this paradox, Dirac proposed the existence of a sea of negative energy states, later known as the Dirac sea. In this model, all negative energy states were already filled, preventing electrons from falling into them. However, if an electron were given enough energy, it could leap out of the Dirac sea, leaving behind a hole. This hole would behave like a particle with the same mass as an electron but with opposite charge, an anti-electron. In 1931, Dirac proposed the existence of antimatter. Initially, he speculated that the anti-electron might be the proton, which was already known to have a positive charge. However, the proton's much greater mass ruled out this possibility. Dirac's anti-electron, later called the positron, remained a theoretical prediction, awaiting experimental confirmation. While Dirac's equations laid the groundwork, it was Carl Anderson who provided the proof. In 1931, Anderson began studying cosmic rays, particles streaming across the universe, using a cloud chamber. This device, filled with water vapor, allowed charged particles to leave visible trails as they passed through. Anderson observed a trail that mirrored those of electrons but curved in the opposite direction under a magnetic field. This indicated a particle with the same mass as an electron but with a positive charge. In 1932, Anderson published his findings, naming the particle the positron. Dirac's theoretical antimatter had become a reality. The discovery of the positron marked the beginning of an era. While positrons could occasionally be found in cosmic rays, other antiparticles were far rarer. Physicists turned to particle accelerators to create antimatter artificially. By colliding particles at high speeds, they converted kinetic energy into mass, producing showers of particles and their corresponding antiparticles. In 1955, scientists at the Bevatron Accelerator at Lawrence Berkeley National Laboratory created the antiproton. A year later, they discovered the antineutron. These discoveries expanded the antimatter catalog and opened new avenues for research. However, creating an entire antiatom remained a daunting challenge. In 1995, nearly 4 decades after the discovery of the antiproton, researchers at CERN achieved a monumental breakthrough. Using the low-energy antiproton ring, they combined antiprotons with positrons to create 9 antihydrogen atoms. This marked the first time an antiatom had been synthesized in the laboratory. Further advancements came in the following decades. By 2010, CERN scientists had developed techniques to trap antihydrogen atoms for extended periods. These experiments allowed researchers to study the properties of antimatter in unprecedented detail. Their findings confirmed that antihydrogen behaved almost identically to regular hydrogen, including its interactions with light. Antimatter holds profound implications for our understanding of the universe. Dirac's work not only expanded the boundaries of quantum mechanics but also raised new questions about the nature of reality. If antimatter mirrors matter so perfectly, why does the observable universe contain so little of it? The apparent asymmetry between matter and antimatter remains one of the greatest mysteries in modern physics. Additionally, antimatter offers tantalizing possibilities for technology. In theory, matter-antimatter annihilation could provide an incredibly efficient energy source. However, the practical challenges of producing and storing antimatter on a large scale remain formidable. Paul Dirac's pursuit of beauty in mathematics led to one of the most significant discoveries in physics. From the theoretical prediction of the positron to the creation of antihydrogen, the story of antimatter exemplifies the interplay between theory and experiment. Nearly a century after Dirac's groundbreaking work, his insights continue to inspire scientists, inviting us to explore the boundaries of the known universe and the mysteries that lie beyond. Where is all the antimatter? Imagine a world where humanity harnesses the boundless power of antimatter. What do you see? Do you envision massive interstellar starships racing through the cosmos, expanding our reach to habitable worlds light years away? Extraterrestrial colonies braving harsh or Eden-like landscapes, staring out at twin suns setting on alien horizons? Or perhaps a far darker vision, desolation, the aftermath of an untamed technology, a power station explosion dwarfing Chernobyl and Fukushima, humanity's frailty magnified by mutual annihilation. These scenarios, both awe-inspiring and terrifying, stem from the immense potential of matter-antimatter reactions, the most fuel-efficient process known in physics. According to Einstein's famous equation, the annihilation of matter and antimatter results in the total conversion of mass into energy. Gram for gram, matter-antimatter annihilation releases energy over 100 times greater than nuclear reactions and 1 billion times more potent than burning fossil fuels. No other process in physics can surpass this efficiency. For now, antimatter propulsion systems, batteries, and warheads remain the stuff of science fiction. Producing and storing antimatter for practical use consumes far more energy than the antimatter itself could release, rendering it unfeasible as a fuel. However, even without imagining futuristic technologies, antimatter is already part of our present, woven into the tapestry of daily life and scientific exploration. In 1940, Canadian chemist Martin Kamen was working at the Berkeley Radiation Laboratory at the University of California. His goal was deceptively straightforward: to create a new isotope of carbon, the elemental backbone of all known life. Together with his colleague Sam Rubin, Kamen irradiated graphite samples, hoping to induce the formation of a previously unknown carbon isotope. For days, they worked tirelessly, with Kamen enduring sleepless nights. One fateful evening, after stepping out for fresh air, Kamen's disheveled appearance caught the attention of a patrolling policeman. Mistaken for an escaped convict involved in a local murder spree, he was detained. Once cleared, Kamen returned to his experiments and finally succeeded. He and Rubin had discovered carbon-14. Though rare in nature, carbon-14 has become a cornerstone of radiocarbon dating, enabling scientists to determine the ages of ancient organic materials. For every trillion carbon atoms in your body, one is carbon-14. Unlike stable isotopes, carbon-14 decays over time, a process that begins when an organism dies. By measuring the remaining carbon-14, scientists can estimate how long it has been since the organism last absorbed this isotope through respiration or consumption. The decay of carbon-14 is a process of balance known as beta decay. During this decay, a neutron transforms into a proton, emitting both an electron and an antineutrino. Similarly, the decay of potassium-40 within your body sometimes produces positrons, the antimatter counterpart of electrons, and neutrinos. This means that all life on Earth, including you, is a natural antimatter factory, generating particles that briefly exist before annihilating with their matter counterparts. The properties of positrons have profound medical applications. In the 1950s, scientists developed a groundbreaking imaging technique, positron emission tomography, PET. By injecting a radioactive tracer into the bloodstream, PET scans track the positrons emitted during decay. These positrons annihilate with electrons, producing pairs of photons with a unique energy signature. Detecting these photons allows for detailed imaging of the body, enabling the diagnosis of medical conditions and mapping of brain activity. PET scans have revolutionized our understanding of how the brain responds to stimuli, from admiring a sunset to listening to a story or gazing at the stars. Antimatter is not confined to our bodies or laboratories, it also exists across the cosmos. Violent astrophysical events, such as supernovae and the collisions of neutron stars, eject antimatter into space. In the 1970s, astronomers detected a cloud of positrons near the Milky Way's center. NASA's Compton Gamma Ray Observatory later discovered a fountain of antimatter stretching 3,000 light-years out of our galaxy. The origins of these phenomena remain mysterious, hinting at undiscovered processes in the universe. Despite its presence, the amount of antimatter detected is vastly smaller than the amount of matter in the universe. This imbalance is crucial to our existence. If matter and antimatter had been created in equal quantities during the Big Bang, they would have annihilated one another, leaving behind a cosmos devoid of stars, planets, and life. Yet the observable universe is overwhelmingly composed of matter, with antimatter largely absent. To understand this imbalance, we must journey back to the universe's infancy. In the moments following the Big Bang, matter and antimatter should have existed in perfect symmetry. But something broke this balance. Theorists propose mechanisms such as baryogenesis, where subtle differences in the behavior of matter and antimatter led to a tiny excess of matter. For every billion particles of antimatter, there was one extra particle of matter. This infinitesimal asymmetry allowed matter to survive, forming the galaxies, stars, and planets we see today. The origins of this asymmetry remain one of the greatest mysteries in physics. Experiments at facilities like CERN continue to probe the properties of antimatter, searching for clues to the processes that shaped our universe. As we deepen our understanding, the story of antimatter reminds us of the delicate balances that underpin existence, from the fleeting positrons within our bodies to the vast cosmic structures born from an ancient imbalance. In exploring antimatter, we do more than unravel the universe's mysteries, we confront the profound question of why we are here at all. The dawn of time, a universe born of imbalance. The mystery of why we exist, why matter triumphed over antimatter, is one of the most profound questions in cosmology, a story that begins in the smallest fraction of a second after time itself began. 1/1,000,000th of a second after the Big Bang, the universe was a roiling sea of unimaginable energy, with temperatures reaching 1,000,000 billion degrees Celsius. There was no matter, no atoms or particles to provide substance to the cosmos. Instead, there was light, energy, and the nascent forces that would govern reality. At this temperature, following the principle of mass-energy equivalence, the energy began to condense into particles. From this sea of energy emerged quarks and their antimatter counterparts, antiquarks. Each quark came into existence paired with an antiquark twin. Alongside them appeared gluons, the particles responsible for the strong nuclear force. In cooler conditions, these gluons would have the power to bind quarks together into protons and neutrons. But the universe at this stage was far too hot. In this primordial quark-gluon plasma, particles zipped around at incredible speeds, colliding and annihilating one another. When a quark encountered its antiquark counterpart, they annihilated, converting back into energy in the form of photons. This process, repeated countless times, created a near-total annihilation of both matter and antimatter. As the universe expanded and cooled, leptons, such as electrons and their antimatter equivalents, positrons, began to form alongside neutrinos and antineutrinos. However, with the falling temperatures, new quark-antiquark pairs could no longer spontaneously arise from the vacuum. The quarks that remained slowed enough for gluons to begin binding them together, forming hadrons, the composite particles that include protons and neutrons. Similarly, antiquarks formed antihadrons such as antiprotons and antineutrons. As hadrons and antihadrons emerged, they too began annihilating each other. Protons and antiprotons, neutrons and antineutrons collided, converting their mass into energy. By the time the universe was 1 second old, the annihilation was nearly complete. For every billion particles of matter, only one survived. The rest, along with their antimatter counterparts, had vanished, leaving behind a universe dominated by light and radiation. Around 100 seconds after the Big Bang, the universe had cooled sufficiently for nucleosynthesis to begin. Protons and neutrons started combining to form the first atomic nuclei, giving rise to the light elements, primarily hydrogen and helium. But this process would not have been possible without the tiny imbalance that left one particle of matter for every billion particles of antimatter. Without this asymmetry, the universe would have been an endless expanse of photons with no atoms, no stars, and no life. Why did matter triumph over antimatter? According to our understanding of the Big Bang, matter and antimatter should have been created in equal amounts, leading to their mutual annihilation. The fact that matter remains is a fundamental violation of balance in the universe. This asymmetry, though crucial to our existence, defies the symmetry expected by the laws of physics. One hypothesis suggests that there might be regions of the universe where antimatter dominates, forming anti-galaxies and anti-stars. Since the spectrum of light emitted by antimatter atoms is identical to that of their matter counterparts, anti-galaxies would be indistinguishable from ordinary galaxies through telescopes. However, intergalactic winds would inevitably carry regular matter into these regions, leading to annihilation events. Astronomers have yet to observe the distinctive light produced by such annihilations, casting doubt on the existence of large antimatter structures. Smaller antimatter objects, such as clusters of anti-stars, might persist, shedding antimatter particles that blend into cosmic rays. These signals, however, are faint and difficult to distinguish amid the noise of the universe's radiation. Most scientists now agree that the answer lies not in hidden antimatter galaxies but in a deeper asymmetry embedded in the laws of nature. The universe, it seems, may not have the perfect balance or symmetry that we once assumed. Processes such as CP violation, a phenomenon where certain particle interactions slightly favor matter over antimatter, could explain the observed imbalance. Experiments at particle accelerators like CERN continue to investigate these subtle asymmetries, offering glimpses into the mechanisms that shaped our universe. The dawn of time was a battleground, a cosmic war between matter and antimatter. From this struggle emerged a universe dominated by matter, where the tiniest imbalance allowed for the formation of stars, planets, and life. Though the reasons for this asymmetry remain elusive, they are a testament to the delicate interplay of forces and particles that define our reality. As we peer deeper into the origins of the universe, we are reminded of how close existence came to never happening at all. The survival of matter over antimatter is not just a scientific puzzle but a profound reminder of the fragile circumstances that make our existence possible. The answers to this enigma, when they come, will illuminate not only the nature of the cosmos but the very foundation of why we are here. An unbalanced cosmos, the journey to understanding asymmetry. What if the universe as we know it had been perfectly balanced? Would matter and antimatter have annihilated one another in the first moments of existence, leaving behind a cosmos devoid of stars, planets, and life? How did the scales tip so slightly, yet so profoundly, in favor of matter, allowing the universe to take shape? These questions have driven some of the most pivotal discoveries in physics, revealing a cosmos where balance is more elusive than it seems. In 1912, Qian Wu was born in a small fishing town north of Shanghai. Unlike most Chinese girls of her time, she received a formal education, attending a school for young women founded by her father. Her brilliance in academics led her to graduate at the top of her class with a degree in physics from the National Central University in Nanjing. Encouraged by her mentor, Dr. Jing Wei Gu, Wu emigrated to the United States in 1936 to continue her studies, earning her PhD from the University of California, Berkeley, in 1940. In 1944, she joined the Manhattan Project at Columbia University, applying her expertise in beta decay to wartime research. By the mid-1950s, she had become a U.S. citizen and a leading expert in nuclear physics. It was her mastery of beta decay that would lead her to challenge fundamental assumptions about the universe. Charge symmetry. This principle asserts that positive and negative charges are treated identically by the laws of physics. For instance, up quarks, positively charged, and down quarks, negatively charged, should behave identically in mass and in nuclear reactions. Parity symmetry, often associated with handedness, parity symmetry suggests that the universe has no inherent preference for left or right. A mirror reflection of a physical system should behave identically to the original system. Time symmetry. This principle dictates that the laws of physics remain unchanged if the direction of time is reversed, with particles flipping their speed and spin as if the universe were rewound. Together, these principles form the foundation of CPT symmetry. If CPT symmetry holds, the universe should behave identically even under transformations of charge, handedness, and time. But what if one of these principles were subtly broken? In 1956, theoretical physicists Chen-Ning Yang and Tsung-Dao Li proposed that parity symmetry might not hold for the weak nuclear force, a controversial idea at the time. Li approached Wu to discuss the possibility of designing an experiment to test this hypothesis. Wu proposed an ingenious method involving the radioactive isotope cobalt-60. Cobalt-60 decays via beta decay, emitting electrons and gamma rays. Wu's experiment cooled cobalt-60 atoms to extremely low temperatures and constrained them within a magnetic field. If parity symmetry were conserved, the emitted electrons would show no preferred direction, even when the magnetic field was reversed. However, Wu's team observed a clear asymmetry. More electrons were emitted against the magnetic field than along it. Nature, it seemed, could distinguish left from right. This groundbreaking discovery, published in December 1956, shattered the long-held assumption of parity symmetry in the weak nuclear force. The universe, at its most fundamental level, was not symmetric. Despite Wu's pivotal role, the 1957 Nobel Prize in Physics was awarded solely to Yan and Li. Nevertheless, Wu's contributions cemented her legacy as a trailblazer in nuclear physics. Wu's work was only the beginning. In subsequent decades, experiments revealed violations of CP symmetry, the combination of charge and parity, in the behavior of quarks and antiquarks. These discoveries showed that the universe treats matter and antimatter differently, albeit in extremely subtle ways. By the end of the 20th century, CP violation was well established, confirming that the cosmos is slightly unbalanced. Could CP violation explain why matter outnumbered antimatter in the early universe? The asymmetry observed in quarks and antiquarks, while significant, is not sufficient to account for the 1 in a billion excess of matter that remained after the Big Bang. Scientists have since turned their attention to other particles, particularly leptons and neutrinos. Neutrinos are among the most enigmatic particles in the universe. Nearly massless and barely interacting with matter, trillions pass through your body every second without a trace. Unlike other particles, neutrinos exhibit a curious asymmetry. All observed neutrinos are left-handed, while all antineutrinos are right-handed. This raises intriguing possibilities. Right-handed neutrinos. If right-handed neutrinos exist, they may have played a role in the early universe, decaying more often into matter than antimatter. Neutrinos as their own antiparticles. Alternatively, neutrinos might be their own antiparticles, capable of annihilating themselves under certain conditions. This property, if confirmed, could help explain the matter-antimatter imbalance. Current research at particle accelerators and neutrino observatories aims to uncover whether neutrinos violate CP symmetry. Preliminary results are promising but inconclusive. If neutrinos indeed favor matter over antimatter, they could provide the missing piece of the puzzle. Another intriguing hypothesis suggests that pockets of antimatter might still exist, isolated from the rest of the universe. Antimatter clusters, such as antistars, could persist in regions far from regular matter, avoiding annihilation. Instruments aboard the International Space Station, like the Alpha Magnetic Spectrometer, are searching for rare antimatter particles, such as anti-helium-3. By studying the abundance of antimatter in our cosmic neighborhood, scientists hope to extrapolate its presence across the universe. The universe's asymmetry is both its mystery and its salvation. Without the slight imbalance that favored matter over antimatter, the cosmos would be a sea of photons, devoid of stars, planets, and life. The discoveries of Chien-Shiung Wu and others have illuminated the subtle ways in which the universe defies symmetry, offering glimpses into the mechanisms that shaped our existence. As we continue to explore these mysteries, each new discovery brings us closer to understanding why matter prevailed and why we are here. The story of the universe's unbalanced nature is not just a tale of physics, but a profound reflection on the delicate conditions that make life possible. What secrets lie in the vastness of the universe? How did the cosmos come to exhibit such astonishing uniformity across incomprehensible distances? Could our understanding of the universe's origins be incomplete, or are we simply witnessing an extraordinary cosmic coincidence? High above the swirling atmosphere of a distant planet, a telescope orbits silently. Its curved mirror collects ancient light, a faint echo of the universe's past. The instrument adjusts, turning its gaze from the bright stars of its local system to the darker, more enigmatic corners of the night sky. Beneath it, the alien world rotates, its white clouds twisting gently under the light of an alien sun. From its vantage point above the atmosphere, this telescope enjoys a clarity of vision unmatched by any ground-based observer, revealing the grand structure of the cosmos. The closest stars, mere light years away, appear as solitary points in the blackness, each a unique sun akin to the one hidden behind the planet below. But beyond these nearby stars lies a sprawling galactic plane, a dense, radiant band that stretches across the sky. This plane marks the center of the galaxy, an immense spiral of stars and interstellar matter stretching over 100,000 light-years and containing some 400 billion suns. Yet the telescope's focus shifts again, peering above the galactic plane where the stars thin out. Here, dim, multicolored smudges paint the sky. Each smear is a galaxy, a collection of billions of stars, their light diminished by the immense distances separating them from the observer. The telescope maps these galaxies with precision, revealing that they are not evenly distributed but instead cluster together in a local group. Beyond this, the instrument detects fainter structures, clusters of galaxies, and even larger superclusters stretching hundreds of millions of light-years, separated by vast, empty voids where no light or matter can be found. At the very limits of its reach, the telescope glimpses the edge of the observable universe. This faint horizon, some 45 billion light-years away, marks the boundary beyond which light has yet to travel to us since the beginning of time. Through this single lens, the structure of the universe is laid bare, an intricate web of galaxies, clusters, and voids, extending outward in all directions. But this telescope is no earthly creation. It orbits a planet far removed from our solar system, circling a foreign sun within a galaxy that is not the Milky Way. Our home, the Earth, lies somewhere beyond its gaze, hidden within the vastness of the cosmos. Yet remarkably, this alien perspective offers a universe that looks strikingly familiar. No matter where you stand in the cosmos, the large-scale structure of the universe remains consistent. The temperature of the cosmic microwave background is uniform. The lumpy distribution of galaxies, clusters, and voids persists. The universe appears isotropic and homogeneous, as if sculpted by some invisible hand to be the same everywhere. This raises a profound question: how can parts of the universe so distant from each other, separated by tens of billions of light-years, be so similar? These regions could never have exchanged information or energy, as light itself has not had enough time to traverse the gulf between them since the beginning of the universe. This horizon problem has challenged cosmologists for decades, pointing to a gaping hole in our understanding of the universe's origins. To unravel this mystery, scientists must journey back to the very beginning of time, to the origins of the universe itself. The prevailing theory, the Big Bang, suggests that the universe exploded into existence 13.8 billion years ago, expanding rapidly from an unimaginably small and dense state. But this explanation alone cannot account for the observed uniformity. Instead, we must delve into the realm of quantum mechanics, where the tiniest fluctuations in the fabric of reality could have been stretched across the universe during an epoch of rapid inflation, a fleeting moment when space expanded exponentially faster than the speed of light. This inflationary model, while elegant, raises new questions. Could our universe be but one bubble in a vast multiverse, each bubble with its own physical laws and conditions? If so, how do we reconcile the apparent uniformity of our cosmos with the chaotic diversity that such a multiverse implies? To answer these questions, we must confront the deepest mysteries of physics. What mechanism drove inflation? Was there truly a bang in the Big Bang, or is this term a simplification for a process far more intricate? Is the observable universe merely a fragment of a grander, more complex reality? Around 13.8 billion years ago, the universe began, or so our best evidence suggests. Yet, despite the clarity of the observations and the elegance of the mathematics, we do not fully understand how it happened. What was the universe like in its very first moments? What forces governed its behavior when it was unimaginably small and incomprehensibly hot? Our theories, based on centuries of observation and logic, offer a compelling narrative, but cracks in this story raise questions that cannot yet be answered. In the 1920s, Georges Lemaitre, a physicist and Catholic priest, proposed that we live in an expanding universe. His calculations, bolstered by Edwin Hubble's later observations of redshifted galaxies, revealed that distant galaxies are moving away from us, their light stretched into longer, redder wavelengths as space itself expands. The further away a galaxy lies, the faster it appears to recede, a phenomenon that could only arise in a universe that has been growing since its beginning. This revelation gave birth to the Big Bang theory, a universe that started small and hot before expanding into the cosmos we observe today. But even as this theory rose to prominence, cracks in its foundation began to emerge. Several perplexing features of the modern universe seem to defy the predictions of a simple, steadily expanding cosmos. These anomalies, known as the horizon problem, the flatness problem, and the absence of magnetic monopoles, present challenges that could undermine the very core of the Big Bang narrative. Imagine standing at one end of an infinite desert and seeing an oasis at the horizon. Now imagine someone at the opposite end of this desert, billions of miles away, observing the same oasis. How could the two ends of such a vast landscape share the same feature? The horizon problem is much like this. No matter where we look in the universe, the cosmic microwave background radiation, the faint afterglow of the Big Bang, appears remarkably uniform in temperature. This radiation suffuses the universe, raising the temperature of space to just a few degrees above absolute zero. For this homogeneity to exist, all regions of the universe must have been in thermal contact long enough to equilibrate, just as a room eventually evens out in temperature when heat is distributed. But here lies the paradox. In an expanding universe, regions separated by billions of light-years are beyond each other's causal horizons. They could never have been in contact to exchange energy or information, even in the earliest moments of cosmic history. How, then, did these distant regions come to share the same temperature? This puzzle suggests an extraordinary degree of fine-tuning in the universe's initial conditions, a statistical improbability that defies the laws of physics and probability. Einstein's theory of general relativity describes space-time as a malleable fabric, warped by the presence of matter and energy. The shape of this cosmic fabric depends on the universe's overall density. If the density is too high, the universe curves into a spherical shape, eventually collapsing under its own gravity. If the density is too low, the universe takes on a hyperbolic, open shape, expanding forever at an accelerating rate. Between these two extremes lies a delicate balance, a flat universe, with just the right density for expansion to slow infinitely over time without collapsing. The odds of the universe naturally achieving this balance are infinitesimally small, akin to flipping a coin and having it land perfectly on its edge. Yet, when astronomers measure the curvature of space, they find it to be astonishingly flat, to an almost unimaginable precision. How could the universe begin with such an improbable density, poised perfectly on this cosmic knife edge? This apparent fine-tuning suggests either an extraordinary coincidence or that our understanding of the early universe is incomplete. In theory, the early universe should have produced a plethora of magnetic monopoles, hypothetical particles that carry a single magnetic charge either north or south, unlike the dipole magnets we are familiar with. These monopoles are predicted by grand unified theories of particle physics and should have been created in abundance during the intense heat of the universe's earliest moments. Yet, despite extensive searches across all scales, no monopoles have ever been found. Their absence poses a direct challenge to our models of the universe's earliest epochs. These three challenges, horizon, flatness, and monopole problems, have forced cosmologists to reconsider the simplicity of the Big Bang model. Could the early universe have undergone a period of rapid inflation, stretching space exponentially in the tiniest fraction of a second? Inflation theory, proposed in the 1980s, offers a tantalizing solution. By expanding the universe faster than the speed of light, inflation could homogenize temperatures across vast distances, flatten spacetime, and dilute any primordial monopoles to undetectable levels. But even inflation raises deeper questions. What caused it to begin, and what caused it to end? Could our universe be part of a larger multiverse, with different regions experiencing their own unique inflations? Are the initial conditions of the universe determined by quantum fluctuations on a scale we cannot yet comprehend? The story of the Big Bang remains a work in progress. It has provided a framework to understand our universe's past and future, but its mysteries remind us of how much we have yet to learn. As we peer deeper into the cosmos and refine our theories, the answers we seek may reveal not only the origins of our universe but also the very nature of reality itself. Alan Guth and the Revolution of Cosmic Inflation. What lies at the very foundation of the cosmos? How did the universe transition from a chaotic, infinitesimal beginning to the structured vastness we see today? These questions, as compelling as they are elusive, occupied the thoughts of Alan Guth on a fateful evening in Menlo Park, California. Late into the night, amidst pages covered in equations and musings, Guth reached a realization that would forever change our understanding of the universe: cosmic inflation. By the late 1970s, Guth was an ambitious physicist facing a fiercely competitive academic world. He had immersed himself in the mysteries of particle physics and the early universe, particularly the conundrum of missing monopoles, hypothetical magnetic particles predicted by grand unified theories. Despite his determination, Guth felt the weight of an unsolved puzzle. Why did the universe appear so uniform and vast, yet seemingly inconsistent with the predictions of the standard Big Bang theory? That evening, inspiration struck. Guth proposed that the universe, in its earliest moments, underwent an extraordinary phase of exponential expansion, a period of cosmic inflation. This profound insight not only addressed lingering questions about the Big Bang but also provided a coherent framework for understanding the large-scale structure of the cosmos. Though the Big Bang model elegantly explained phenomena such as the cosmic microwave background radiation, CMB, and the relative abundances of light elements, it left critical gaps in our understanding of the universe. The CMB, the faint afterglow of the Big Bang, exhibits an almost perfect uniformity in temperature across the sky. However, in a universe expanding at a constant rate, regions separated by vast distances should never have been able to exchange energy or information. How, then, could they have reached such thermal equilibrium? Einstein's general relativity suggests that the geometry of the universe depends on its density. A slight deviation from the critical density would lead to a universe that either collapses in on itself or expands uncontrollably. Yet observations reveal a universe that is astonishingly flat, defying expectations without extraordinarily fine-tuned initial conditions. Grand unified theories predict the formation of magnetic monopoles in the early universe. These particles, if they existed, should be abundant. However, despite extensive searches, no monopoles have ever been observed. This glaring absence remained a major challenge for cosmologists. Guth's theory of inflation proposed that the universe underwent a period of rapid exponential expansion within the first tiny fraction of a second after the Big Bang. This dramatic growth smoothed out irregularities, resolved inconsistencies, and created the conditions for the cosmos we observe today. Inflation was driven by a scalar field, a theoretical energy field that permeated the early universe. This field became temporarily trapped in a high-energy state, driving rapid expansion. When the field transitioned to a lower energy state, it released immense energy, reheating the universe and producing the particles and forces we observe today. The implications were staggering. In a mere 10 superscript 3 seconds, the universe expanded by a factor of 10 superscript 3. A region smaller than a proton balloon to a size comparable to a grapefruit. This exponential growth provided a natural explanation for the universe's vastness and uniformity. Before inflation, the entire observable universe was a tiny, connected region where thermal equilibrium could be established. Inflation then stretched this region exponentially, explaining why the CMB appears so uniform across vast distances. Inflation flattened any initial curvature in the fabric of spacetime, much like inflating a balloon smooths its surface. This process naturally explains why the universe appears so flat, without requiring improbable fine-tuning. In the early universe, monopoles may have been created in abundance. However, inflation diluted their density by stretching space, rendering them so sparse that none are detectable within the observable universe. While Goose's initial model was groundbreaking, it required refinements to align with observations. Physicists such as André Linde and Paul Steinhardt introduced new models of inflation, including chaotic inflation and new inflation, which provided more robust mechanisms for the onset and conclusion of inflation. One of the most provocative implications of inflation is the possibility of a multiverse. In some models, inflation never completely ends but continues indefinitely in isolated regions, creating bubble universes with distinct physical properties. Our universe would then be one of countless others, each with its unique characteristics. Inflation makes several testable predictions, which have been supported by observations. Primordial gravitational waves, ripples in spacetime generated during inflation, leave subtle imprints on the polarization of the CMB. While definitive detection remains elusive, experiments such as BICEP-2 and future observatories aim to uncover this evidence. Quantum fluctuations during inflation were stretched to macroscopic scales, seeding the formation of galaxies and clusters. Observations of the cosmic web align remarkably well with these predictions. Alan Goose's theory of cosmic inflation revolutionized our understanding of the universe's origins. It provided a coherent solution to long-standing problems, connecting the smallest quantum phenomena to the grandest cosmic structures. Yet, as with any transformative idea, it raised new questions. What triggered inflation? What caused it to end? What lies beyond the observable universe? As experiments probe deeper into the cosmos and theories evolve, we move closer to answering these profound questions. Goose's work stands as a testament to the power of human curiosity and imagination, reminding us that the quest to understand the universe is as infinite as the cosmos itself. Outside, the temperature has plunged below -50 degrees Celsius, and the howling winds batter the curved walls of the station. The starlight alone illuminates the icy expanse, a stark and unyielding landscape. Yet, within the heavily insulated control room, a faint mechanical hum from a giant microwave telescope signals the relentless pursuit of understanding. Perched at nearly 3,000 meters above sea level on the high Antarctic plateau, the telescope scans the cosmos with unparalleled clarity, its mission to detect the faint imprints of inflation embed. Inflation, for all its elegance and problem-solving prowess, remains an unproven hypothesis. Its mathematical beauty has captured the imagination of the scientific community, providing a unifying framework that bridges particle physics and cosmology. Yet the ultimate proof of its occurrence lies in the details /U 2014 in the elusive remnants of that moment of extraordinary expansion. To understand the stakes, one must appreciate what inflation promises to explain. The universe, vast and structured as it is, arose from what appears to be practically nothing. On the largest scales, it exhibits remarkable uniformity in temperature, yet its matter is distributed unevenly /U 2014 galactic superclusters juxtaposed with immense voids. This contrast, the very fabric of the cosmos, poses a profound question: how did such complexity emerge? The answer may lie in the quantum realm. On the smallest scales, quantum particles behave unpredictably, their existence governed by Heisenberg's uncertainty principle. Virtual particle pairs spontaneously flicker into and out of existence without cause or effect. In the pre-inflationary universe, small enough to be dominated by such quantum effects, these fluctuations played a pivotal role. When inflation began, the rapid expansion stretched these tiny variations to macroscopic scales, seeding the large-scale structures we see today. From quantum noise, the architecture of the cosmos was born, feat so remarkable that Alan Goose famously called it the ultimate free lunch. The Antarctic scientists of 2013, armed with the BICEP-2 telescope, sought to verify this remarkable story. Their focus was on B-mode polarization, subtle patterns in the cosmic microwave background radiation that could only arise from the gravitational waves generated during inflation. When the team announced the detection of these B modes in March of that year, the scientific world erupted with excitement. At last, it seemed, inflation had found its definitive proof. Yet science demands rigor, and as months passed, the initial confidence in the discovery waned. Cosmic dust in the polar sky, it turned out, could produce similar polarization patterns, casting doubt on whether the observed signals truly originated from inflation. The search for unequivocal evidence had hit a stumbling block, but the quest continued undeterred. Inflation's predictive power extends beyond the cosmic microwave background. Theoretical models suggest that it could generate primordial black holes, relics of the chaotic early universe formed less than a second after the Big Bang. These black holes, if discovered, would not only validate inflation but also offer insights into its mechanisms. Intriguingly, some theories propose that these primordial black holes might harbor entire baby universes. Isolated from our cosmos by the limits of their observable horizons, these universes would appear as singularities to us. Within them, however, their inhabitants would experience an expanding cosmos much like our own. Such a nested multiverse, hidden in the depths of black holes, challenges our understanding of existence and raises philosophical questions as profound as the scientific ones. At the heart of inflation lies the inflaton field, theorized to drive the rapid expansion of the early universe. Its existence is tied to a hypothetical particle, the inflaton, which remains elusive. This parallels the long search for the Higgs boson, which took nearly 50 years from its theoretical prediction to its discovery in 2012. The detection of the inflaton would mark a monumental leap forward in cosmology, connecting the quantum underpinnings of inflation to the large-scale structure of the universe. Despite the challenges, scientists remain optimistic. The tools of observation continue to evolve, and theoretical frameworks grow more robust. If inflation truly shaped the cosmos as we know it, its signatures are out there, waiting to be found. Whether in the faint polarization of ancient light, the discovery of primordial black holes, or the eventual detection of the inflaton, the proof of inflation grandeur lies just beyond the horizon. Inflation is both a triumph and a mystery. It elegantly explains the origins of the universe's vastness and structure, yet its mechanisms remain shrouded in uncertainty. For the Antarctic scientists braving the eternal night, the burden of proof is not a deterrent but a call to exploration. As they peer into the cosmos, they are driven by the same unyielding curiosity that inspired Goose's groundbreaking realization decades ago. In their work lies the hope that one day, the story of inflation will be fully written, not just as a theory but as an undeniable truth etched into the fabric of spacetime itself. Until then, the search continues, fueled by the belief that the universe, in its infinite complexity, will one day reveal its most profound secrets. In a lively bar near the University of Pennsylvania, Paul Steinhardt once raised a glass in celebration. His latest paper, Advancing the Burgeoning Theory of Inflation, had been accepted for publication. It was a moment of triumph, yet his mind was restless. Even as his peers discussed the promise of inflation, doubts began to creep in. The models he and his colleagues had painstakingly developed were mathematically sound, but their implications troubled him. For inflation to work, the parameters needed to be chosen with almost implausible precision. Without this fine-tuning, the model produced bizarre outcomes, chaotic multiverses of tangled, knotted space-time. Steinhardt's unease grew with time, and today he has become one of inflation's most vocal critics. What was once his triumph has now become his target. Inflation was initially proposed as a solution to fundamental problems in cosmology. It explained how the early universe could have reached the observed levels of homogeneity and flatness without requiring an improbable degree of fine-tuning in its initial conditions. By positing an era of rapid exponential expansion just after the Big Bang, inflation smoothed out irregularities and flattened spacetime. For decades, it provided a coherent narrative for the cosmos' large-scale structure. Yet Steinhardt argues that inflation has introduced as many problems as it sought to solve. For one, the sheer variety of inflationary models has made the theory increasingly untestable. The parameters of inflation can be endlessly adjusted to fit almost any observation, rendering it, in Steinhardt words, pseudoscientific. A theory that cannot be falsified ceases to be a scientific theory at all. Moreover, inflation success depends on the same kind of fine-tuning it was meant to avoid. Steinhardt analysis of the cosmic microwave background fine-scale structure revealed that only an infinitesimally small fraction of inflationary models could produce the universe we observe. The odds were so minuscule /U 2014 less than 1 in a googolplex /U 2014 that Steinhardt found himself questioning the entire framework. One of inflation's most contentious implications is the multiverse. In most inflationary scenarios, the process does not stop uniformly. Instead, different regions of space continue to inflate at different rates, creating a chaotic multiverse of bubble universes. While this idea is theoretically fascinating, it raises profound philosophical and scientific issues. If we exist in just one bubble, isolated from the others, how can we ever test the existence of these other universes? More troublingly, the chaotic nature of the multiverse challenges the idea of a coherent, comprehensible cosmos. Inflation was meant to provide simplicity, yet it seems to have spawned complexity on a scale that defies reason. For Steinhardt, the multiverse is not a feature but a flaw symptom of a theory stretched beyond its breaking point. Despite these criticisms, there is no clear replacement for inflation. Alternative models have been proposed, each offering intriguing possibilities but also grappling with their own limitations. Steinhardt himself has revisited the idea of a cyclical universe, Big Bounce, model in which the cosmos undergoes endless cycles of expansion and contraction. This approach, rooted in George Lima Phoenix universe, could resolve some of inflation problems, particularly the fine-tuning issue, if the entropy dilemma can be addressed. Other theories suggest that our universe birth was a ripple in a higher dimensional bulk of hyperspace, or that fundamental constants like the speed of light might have behaved differently under extreme conditions. These ideas, while captivating, are currently beyond the reach of experimental validation. The physics they invoke lie at the edges of our comprehension, tantalizing but elusive. For all its flaws, inflation remains the dominant paradigm in cosmology. Part of its appeal is its ability to be framed within the boundaries of known physics. Unlike some alternatives, which require entirely new frameworks, inflation can be described using the tools we already possess. This makes it a comfortable, if imperfect, solution for many scientists. Yet Steinhardt warns against complacency. He believes that the scientific community's reluctance to confront inflation shortcomings risks turning it into a dogma. To move forward, cosmologists must critically examine not only the theory itself but also their own assumptions and biases. The debate over inflation is far from settled. As observational techniques improve and theoretical models evolve, the next decade may bring clarity to these cosmic mysteries. Whether inflation is vindicated or replaced, the process of questioning and refining our understanding will drive progress. Paul Steinhardt dissent is a reminder that science thrives on skepticism. Theories, no matter how elegant or widely accepted, must withstand scrutiny. The cosmos may still hold secrets that defy our imagination, but the quest to unravel them is what defines our pursuit of knowledge. In the end, the history of the universe is not just a story of stars and galaxies but of human curiosity and the relentless search for truth.